Hello, I'm Ellen Stofan, the John and Adrienne Mars Director of the Smithsonian's National Air and Space Museum. Thank you for tuning in to tonight's John and Bacall lecture, which turns our eyes to the heavens each year, covering exciting topics in astronomy. This year, our lectures take a look at perhaps our most productive observatory ever. The Hubble Space Telescope has not only brought us data that has changed our fundamental understanding of the universe, but also brought us images that create wonder and joy and inspired others to seek to understand the stars. Our speaker tonight is David LaCrone, Emeritus Senior Scientist at NASA's Goddard Space Flight Center. Marking Hubble's 30th anniversary, he'll discuss several long threads of discovery that were made possible by Hubble's extended lifetime and regular modernization over those 3 decades. Before we start that exciting discussion, I'd like to acknowledge our sponsors who make the Bacall Lecture possible. Thank you to the Space Telescope Science Institute and the Hubble Space Telescope Project, NASA Goddard Space Flight Center, for their support of this program, especially as we adapted it to bring it into your homes tonight. Now, I'd like to turn it over to David Dvorkin, Senior Curator of the History of Astronomy and the Space Sciences, to introduce you to David LaCrone and the ongoing legacy of Hubble that he's talking about tonight. David.
Hi, everybody. My name is David Dvorkin, and I'm the Curator of Astronomy here at the National Air and Space Museum. And on behalf of the museum, Dr. Stofan, I want to welcome everybody to the 2020 John N. Bacall Lecture. Tonight, I'm especially delighted to be able to introduce Dr. David LaCrone, who will speak to us about Hubble at 30. Now this year, we're celebrating, in fact, the 30th anniversary of the launch of the Hubble Space Telescope. And for 3 decades, thousands of astronomers from around the world have used the remarkable capabilities of this telescope and its scientific instruments to revolutionize our understanding of the universe. Even though it has been over 10 years since the last servicing mission, the observatory remains highly productive and reasonably healthy. One might say that Hubble has established the paradigm for a long-lived mountaintop observatory in space. So tonight, Dave LaCrone, who is the Emeritus Senior Scientist at NASA's Goddard Space Flight Center, will look back over these 30 years and review several fascinating discoveries that were made possible by Hubble's extended lifetime and, most importantly, its regular modernization. You might say Dave LaCrone is a real deal Hubble expert. He worked as an astrophysicist at NASA's Goddard Space Flight Center for some 40 years, and 33 of those with the Hubble project. From 1992 to 2009, Dave was Hubble's senior project scientist. He provided scientific leadership for all aspects of the Hubble program, including program management, spacecraft and science operations, development of new scientific instruments, and in-orbit servicing. He had overall project responsibility to assure that the scientific performance requirements for the Hubble Observatory were achieved and that the Hubble remained scientifically productive and successful over its long lifetime. Dave also supervised, as chief project scientist, NASA's 5 highly successful servicing missions. That's a real legacy. He earned a Bachelor of Science in Physics from Purdue University in 1964 and a PhD in astronomy from UCLA in 1969. Dave and I are, in fact, friends. We became friends at UCLA. I was then a senior. Dave has been recognized for both his scientific and project work many times. And in 2009, he received the NASA Distinguished Service Medal, the highest honor the agency bestows on a civil servant. Dr. LaCrone retired from NASA in 2009. So tonight, we are honored to have David lead this conversation as we celebrate 30 years of exploring the universe with the Hubble Space Telescope. So David, please take it away.
Thank you, David, and good evening. I'm deeply honored to have been selected to give the John N. Bacall Memorial Lectures for 2020, the year of Hubble's 30th anniversary. This is John. John, for much of his professional career, was a tireless and passionate advocate for the Hubble Space Telescope. in the astronomical community, within NASA, and particularly on Capitol Hill in the US Congress, persuading people why it was important that we have this new advanced technology capability in space. So John was a good friend. He died too young in 2005. He continued to advocate for Hubble up to the time of his death, actually. And he was a good colleague, a good friend, and a wonderful person to work with all those years. The plan for tonight is that I'm going to limit my talk here to a relatively brief period of time, 25 minutes or so that we would have plenty of time for questions and discussion at the end. So if there's something that I say or that you see in my slides as I go along that tweaks your interest, please feel free to ask a question, and we'll try to discuss it further a little later. First, some Hubble history. Hubble, of course, was launched in 1990 on shuttle Discovery, and within a month after its launch, we discovered that we simply could not bring the telescope into focus. This is a galaxy image looking very blurry. An image of an individual star had a lot of wasted light out in this apron. We just couldn't bring it into focus. The problem was that the primary mirror, the 94-inch diameter primary mirror of Hubble, had been ground to the wrong prescription. Too much glass had been removed from it. So Hubble had an anomaly called spherical aberration. Some very brilliant people over the next year or so came up with means for correcting, for exactly offsetting the error in the primary mirror, so that the scientific instruments on Hubble would never know that the instrument, that the telescope beam was spherically aberrated. Wide Field Planetary Camera 2 was a spare workhorse camera for Hubble that we were already in the process of building. So simply by replacing 4 small nickel-sized mirrors with correct figure on them, in WFPIC 2 we could correct for spherical aberration, and that took care of about 50% of our science program. Then another very clever device called COSTAR, Corrective Optic Space Telescope Axial Replacement, actually could be deployed to insert pairs of small nickel-sized mirrors into the telescope beam, and the shape of those mirrors would be such as to exactly offset the incorrect shape of the primary mirror to give us perfectly focused images. So the idea was to launch these new capabilities on a first servicing mission, more or less a call-up or emergency mission in December of 1993. You see image here of astronaut Jeff Hoffman removing the old Wide Field Planetary Camera, which looked very much like the new one that was inserted then by he and Story Musgrave. Here you see KT Thornton and Tom Akers installing the COSTAR device in the back end of the telescope. And within a month or so after the servicing mission 1 was flown, this is what those same images looked like. A very sharply focused, beautiful image of the central region of a galaxy, spiral galaxy, and a point source image of a star that was very tightly focused. Once we had corrected spherical aberration, life was very, very different for Hubble people. No matter where we pointed the telescope in the sky, it seemed like we were able to see things that no human had ever seen before. Incredible clarity, incredible beauty, and many surprising things. We were lucky in 1994, within about 6 months after the first servicing mission, to be online to be able to observe the spectacular crashes into the atmosphere of Jupiter of 21 fragments of comet Shoemaker-Levy 9, producing impact zones that looked a bit like, well, looked just like this in the upper atmosphere of Jupiter. It also in 1994, one of our first spectrographs, the faint object spectrograph, was able to verify that a supermassive black hole, about 3 billion times the mass of our sun, existed in the nucleus of a large galaxy called M87. In 1997, when we launched the Space Telescope Imaging Spectrograph, we called it the Black Hole Hunter because, as its name implies, it was designed to go looking for supermassive black holes inside galaxies. And this is what the signature of such a supermassive black hole would look like, this characteristic S-shaped signal in a STIS spectrum. Those data from STIS demonstrated for several dozen supermassive black holes that the mass of the black hole seemed to be correlated with the mass of the system of stars in which it was contained, even though the system of stars knew little about the black hole, and the black hole knew nothing about the stars gravitationally. A real puzzle. One of the important things that was done when spherical aberration was corrected was a key project to recalibrate the distance scale of the universe to much greater accuracy than ever before, and determine how rapidly the universe is expanding and how old the universe is. And to do that, we used variable stars, a class of variable star called Cepheid variables. You see here that we could find now with Hubble's great clarity of image, we could find these Cepheid variable stars amongst the stellar populations of other galaxies, and thereby determine the distances to those galaxies. As the Cepheid variables changed in brightness from bright to faint to bright to faint, the periodicity of those changes, how long it took to go through one of those cycles, was directly related to how intrinsically bright the Cepheid was, and therefore gave us a good indicator of how far away it was and how far away the galaxy was that it occurred in. A different kind of standard candle, an exploding star, a certain class called type 1a supernovae, allow us to extend the distance the improved distance scale, even farther out across the universe. You see an example here. The little dot at the right there, separated from its parent galaxy, is the exploding star, very clearly resolved in the Hubble image. And one can measure how the brightness of that exploding star varied with time. And from that variation, you could tell how far away it was. In the ground-based image, you could barely make it out as a little bulge in this blurry image. Putting together the Cepheid distance scale improvement and the type 1a supernovae distance scale improvements, one can make a graph that looks something like this. Down here at distances relatively close to us, at velocities of recession of the expansion of the universe, at relatively low velocities, you see a straight line relationship. That's called Hubble's law. And the slope of that straight line is the Hubble constant. It's the rate at which the universe is expanding at the present time. If you extend Hubble's law farther out across space and back in time, if the same law, if the universe was expanding at the same rate, no matter how far out you looked, that straight line would just continue and the data would fall right along it. In fact, what was observed was the observations of the really distant galaxies using the type 1a supernovae fell below a straight line, which meant that in times past, the farther out across the universe you looked, the expansion of the universe was slower than it is today. Another way of saying that is the universe is expanding faster today than it was a long time ago. And as a consequence of that, we can now say the expansion of the universe is accelerating. This is a huge surprise in astronomy and physics. It gave us many puzzles to chew over. No one really understands why the universe is accelerating in its expansion, but it did give a Nobel Prize to Hubble observers, a Nobel Prize in physics in 2011. So the first really regularly scheduled servicing mission that didn't involve some major crisis like spherical aberration took place in 1997, February. It was Servicing Mission 2, SM2. We put on 2 brand new instruments, high technology instruments. I've already mentioned the STIS instrument, the Black Hole Hunter here, and our first infrared instrument, NICMOS here, near infrared camera and multi-object spectrometer is what that means, but it's primarily an infrared camera. And here you see just an image of an astronaut installing STIS during SM2 in the back end of the telescope. It was on this mission that we noticed that Hubble had a sunburn on the side of the telescope that normally faces the sun in its orbit. We were starting to see degradation in the multi-layer insulation that covers the telescope and helps keep it thermally controlled. You see here a big rip. There were cracks, there were crinkles. It turns out that they really didn't have a bad effect, at least in the near term, on the thermal control of the telescope. But during that mission, the astronauts very cleverly came up with some jury-rigged patches that they could use to cover areas like this to give the telescope some protection until we could do something more permanent later. Now, I mentioned a rescue. In 1999, we actually had Hubble go down for about 6 weeks where it wasn't doing science. If you see these three silver-colored boxes in the aft shroud of the spacecraft, each of those boxes contains two gyroscopes, and the gyroscopes are essential for pointing Hubble accurately and keeping it stable on its targets. And we carry 6 gyroscopes. Originally, we would operate 3 at a time and keep 3 as spares. In the first decade of Hubble's life, you had to have 3 gyroscopes operating, or you simply couldn't use the telescope for science. And late in 1999, in fact, it was about November, I believe, the 4th gyroscope failed. So we had 2 operating and no more spares, and Hubble went down. Fortunately, the prior spring, we had anticipated this might happen and began planning for an emergency servicing mission, which we flew around Christmas time of 1999, and the astronauts replaced all of the gyroscopes and allowed Hubble to come back up to operation shortly thereafter. The next servicing mission was in 2002. We called servicing mission 3B. To do the gyroscope replacement, we had split servicing mission 3 into 2 parts, 3A and 3B. So we finished up the work of SM3 in 2002 on this particular mission. We installed a wonderful new camera, the Advanced Camera for Surveys, which in fact was significantly superior to the Wide Field Planetary Camera that had been our workhorse for so many years. The Wide Field Planetary Camera is a 2 megapixel camera. The ACS was a 16 megapixel camera, much higher resolution, wider field of view, much greater sensitivity. Here's a typical example of an ACS image taken with this new camera. This is called the Tadpole Galaxy. It's really 2 galaxies in collision with each other that has produced this long tail stream of stars. Now, I mentioned in my abstract of this talk that I have Hubble heroes, and I only really have time to give one example. So these people are my heroes, and I'll tell you why. On the same servicing mission, 3B, we had to replace the power control unit on Hubble. The power control unit is the central electrical switching box. And the rub is that to replace it, to take it out, put in a new power control unit, you have to turn the telescope and the spacecraft completely off. All the electricity has to be zeroed out. And when you do that, the risk is that the telescope grows colder. It's no longer got the heating elements electrically powered to keep it warm. So it got colder and colder and colder. Also, without electrical power, you had no telemetry. So you couldn't monitor what was going on inside the telescope. So the critical thing was to choreograph this change out, to have the astronauts get out as quickly as possible, get the old unit out, get the new unit plugged in, and get the telescope turned back on as expeditiously as you possibly can. Unfortunately, in the lead up to the egress of the astronauts out into the payload bay to begin this task, one of the astronauts, John Grunsfeld, had a spacesuit that sprung a leak, a water leak in his cooling system. And it took about 2 hours to take this old the leaky spacesuit off and reconfigure another spacesuit so that John would fit into it and get it back onto him so they could get out and go to work. Meanwhile, the telescope is getting colder and colder and colder because the power has been turned off. That's where my heroes come in to play. Back at the Space Telescope Operations Control Center at the Goddard Space Flight Center, a team of thermal engineers and Bill Crabb, the guy who was sort of in control of the shift, basically threw out the script, turned off the autopilot, took manual control of things, and flew by the seat of their pants. Now, it wasn't exactly totally by the seat of their pants. The thermal engineers had a couple of years of experience running computer thermal models, so they knew how rapidly different components and different instruments of the telescope were getting cold, at least how rapidly they were predicted to be getting cold. So they were able to advise Bill Crabb as to which instruments or which boxes to begin turning on first to partially power the telescope back up so that things didn't break, they didn't reach the red limit. And in the course of time, during the 2-hour period that it took to get John Grunsfeld into a new spacesuit, these folks saved the telescope. They kept Hubble from breaking. They kept its scientific instruments and other components from breaking. And so they're my Hubble heroes. One of many stories. And we had some difficult years starting in 2003 with the loss of Shuttle Columbia and its crew and the tragic disintegration of the vehicle as it tried to re-enter on February 1st of 2003. Shortly thereafter, the administrator of NASA, Sean O'Keefe, canceled our final servicing mission to Hubble. He wanted the shuttle to be used entirely to complete construction of the International Space Station. He thought that it was entirely too risky to send a shuttle in a standalone mission to Hubble. If you go to the space station and there's a problem, the crew can basically survive on the space station as a lifeboat until another mission can be mounted to rescue them. But he didn't think that could be done in Hubble's case, and he didn't want to take that risk of losing another astronaut crew. Now, just within a week after he made that decision and announced it, Senator Barbara Mikulski from Maryland, who is the ranking member, I believe, on the Appropriations Committee that handled NASA's budget and therefore had some sway in the question, disagreed in a letter to Sean O'Keefe, disagreed with this decision, saying no one person should make such a portentous decision. And so she requested that there be a formal study of the risks versus benefits and the safety aspects of flying another mission to Hubble. So Sean O'Keefe, to his credit, relented and asked the National Academy of Sciences to put together a committee to study those questions. Meantime, a man named Frank Sepulina, we all call him Seppi, who is the godfather, actually, of servicing orbiting satellites. He invented the discipline. He was the head impresario to mount all 5 Hubble servicing missions. He was the lead manager for Hubble servicing and for the development of the new instruments and other components of the telescope. He had the bright idea, let's try to service Hubble robotically. Let's find a telerobot that could be sent up on a spacecraft, attach itself to Hubble, and actually do maybe up to 70% of the work that astronauts could have done had they gone up. So this is a mission concept for that telerobotic mission. This is the robot right here. It's called Dexter. And in fact, this robot is in fact actively used on the International Space Station today. At the end of the year-long study, it was determined that really a lot of great engineering had been done, but the technology really wasn't in place yet. It was just too risky, and by the way, probably too expensive to mount a telerobotic mission. Meanwhile, Sean O'Keefe had resigned from NASA, had retired, and at the end of 2004, and in the spring of 2005, NASA appointed Mike Griffin to take Sean O'Keefe's place as NASA administrator. Now, Mike Griffin didn't dismiss, he was not dismissive of Sean O'Keefe's worry about safety, but he asked for a new study of the engineering details of what made these missions safe or what put them at risk. And at the end of the day, he concluded that it was no riskier to send another servicing mission to Hubble than it was to send a shuttle mission to the International Space Station. And on Halloween of 2006, he reinstated Hubble's final servicing mission, much to our relief. One thing that made it safe to fly is that at the time, this is launch day, May 11th, 2009, and you may or may not be able to see in this image, there are actually 2 shuttles on the launch pads. This is Shuttle Atlantis, which was our primary vehicle containing our crew and our equipment. Off in the distance is Shuttle Endeavour, waiting to serve as an emergency mission in case these guys ran into trouble. You could launch, this shuttle could be made to be ready to fly in about 30 days. And meantime, in orbit, these guys can cut their power back and survive for 30 days until the other astronaut crew could come and rescue them. The probability of actually having to do that, we knew, was very low indeed. But it made everybody feel better, I think, to know that that was a backup possibility. And of course, it was not needed. We had a very successful launch of Atlantis on servicing mission 4. Now on servicing mission 4, we replaced, after 15 years of yeoman labor, WFPIC 2 was replaced with a brand new camera called Wide Field Camera 3, which was a superb camera and today is the most highly demanded instrument on the observatory. One aspect of this camera that was a new wrinkle is that it had a very powerful infrared channel, significantly better than the old NICMOS infrared instrument we had flown in 1997. And so it extended our reach into the infrared wavelength range where human beings would sense electromagnetic radiation more as heat than light. And that opened up a lot of different scientific possibilities with the telescope that we didn't really have before. Here's another image replacing the old COSTAR that was no longer needed with another new spectrograph, the Cosmic Origin spectrograph. And just some quick examples of some of the science these new instruments could do, which I'm not going to dwell on right now. In addition to providing 2 brand new instruments to the observatory, for only the second time in history, the astronauts actually were able to repair 2 old instruments that had failed. The Space Telescope Imaging Spectrograph failed in 2004. A high voltage power supply went out of order. And similarly, the Advanced Camera for Surveys that we had put in the telescope in 2002 had failed in 2007. And it also had a high voltage power supply issue. And the astronauts were actually able to open up the instruments, take out faulty circuit boards and replace them with new circuit boards, brought both instruments back up to operation. And so in effect had 4 new instruments, the 2 new that we had put on in that mission and the 2 repaired that were back up and running. This image up here on the upper right-hand corner is humankind's last view of Hubble as Shuttle Atlantis backed away after the deployment of the telescope back into orbit. And this is the crew, terrific crew of people that had conducted this very successful mission, having landed at Edwards Air Force Base in California. Now, I'd like to give a couple of examples of what I call long threads of science. 30 years is a long time. Instruments lasting for 15 or 20 years, that's a long time for a scientific instrument to continue to work well. So one way of doing long thread of science is what I call technology-driven science. And a great example of that are the Hubble Deep Fields. The idea is that each time you put a new camera on board the telescope that's more powerful than the cameras that preceded it, then you go back and redo a Hubble Deep Field. You go back to the same or similar pointing in the sky and just let it crank for a week or 2. And millions of seconds of exposure time. So in this example, the original Hubble Deep Field was obtained in 1995 with the Wide Field Planetary Camera #2, and it reached back out across the universe about 12.2 billion light years. In other words, the look back time was about 12.2 billion years. When the Advanced Camera for Surveys was added to the telescope in 2002, we did the Hubble Ultra Deep Field over a period of time spanning 2003 and 2004. It reached back to about 13 billion light years. Then with the new infrared channel on the Wide Field Camera 3, we did it again and reached back to about 13.2 billion light years. And then an astronomer named Garth Illingworth and his team took all of the observations that had been made on the same field from 2002 through 2013, piled them all together into a single long time exposure, which reached back to 13.3 billion years. I should comment that at the present time, our understanding is that the age of the universe is around 13.8 or perhaps 13.7 billion years. So this was within 400 or 500 million years of the Big Bang. So this is just the idea. Early observations reach this far out in the universe, then the Advanced Camera for Surveys goes a little farther. The infrared channel and LIFT-C3 goes a little farther. And we hope that the James Webb Space Telescope, to be launched next year, will actually probe much deeper out into the early epoch of the universe when new stars and galaxies were just being born. So what have we learned from these deep field observations? The universe, as far out as we can see, is full of galaxies, a few hundred billion of them. Perhaps between 200 and 500 billion galaxies populate the visible universe. We've seen that galaxies form hierarchically. They start out as small clumps of gas and newly born stars and collide with each other. Long time ago, the universe was a smaller place than it is today. And it was much easier for objects to collide with each other. It happened more frequently. As the universe expanded, that happened less and less frequently. But during the course of this process, the hierarchical formation of galaxies, small protogalaxies collided to form bigger and bigger ones. Eventually, as stars formed, the rate of star formation started slowly. It reached a peak a few billion years, perhaps 2 to 3 billion years after the Big Bang, and then fell steadily after that, both as the size of the universe got so large that collisions became rare, and also as the raw material for making new stars was used up. Now, I see I'm a little bit short on time, so I'm going to skip the next topic that I might have talked about had I spoken even faster. And I want to go on to Hubble today. So 30 years after its launch and 11 years after its last servicing call, Hubble's healthy and is operating well. The systems that had degraded or failed over the years have been either repaired or replaced. The major life-limiting items on the telescope continue to be our gyroscopes. These days, we can actually operate and do science on Hubble with only one gyroscope because of the computer power we have on board. Currently, 3 out of 6 gyroscopes remain in operation and 3 have failed. So basically, we have 2 spares. Hubble now has 4 superb scientific instruments still operating at or near the state of the art, pushing back the frontiers of our understanding of the universe. And we expect Hubble to continue stretching these boundaries of our understanding for years to come, hopefully, especially to overlap with the James Webb Space Telescope for several years, as the 2 observatories complement each other nicely. And with that, oh, by the way, before I stop talking, I would like to do a shameless plug for my new book, which has just been published within the last month. It's called Life with Hubble. You can see at the bottom of this chart the website. It's published by IOP Publications. And so you go to https://store.ioppublishing.org, and you can purchase either an ebook copy or a hard copy. And with that, I believe it's time to take some questions.
Well, thank you, David, for a wonderful talk. And thank you to those of you who have tuned in for joining us. This is a live Q&A, and I want to make sure that viewers know that if you have questions, you can put those in the chat that's on the same page as the video. And also, please, along with your question, tell us where you're watching from. So my name is Matthew Schindel. I'm a space history curator at the National Air and Space Museum, and I'm going to be moderating the Q&A. After you give us your questions, I will then ask Dr. LaCrome to answer them. So David, first question. Our first question comes from a National Air and Space Society member. Thank you for being a member. Has the Hubble received any severe erosion over the years in space, or is it not really possible in zero gravity? Now, I'm guessing that maybe the sunburn that you mentioned is the answer to this question.
Yeah, that's one type of erosion would be, it's actually a result of solar particles impinging on Hubble, ultraviolet light impinging on Hubble, the tiny bit of atomic oxygen that is at very high altitude where Hubble is in orbit can attack the surfaces. Yeah, so that's one example of a sort of erosion that has degraded the surface. The other example would be micrometeorites. And yes, one can find on the surface of Hubble little pits that are the result of meteorite impacts and or meteoroid impacts. And but so far, those have not had an effect on our operation in any way.
We have another question from a National Air and Space Society member. With adaptive mirror technology, what do you see beyond Hubble and Webb? What's going to be the next big step after Webb?
Well, we have other great observatories in design and in development right now. The next one after Hubble and Webb is the so-called Roman Space Observatory. It was called W first, but it has recently been renamed in honor of Nancy Grace Roman, who was the founding mother of the Hubble Space Telescope within NASA and advocated as strongly as anyone else to get Hubble created. So the Roman Space Telescope is coming next. There are discussions, of course, of very, very large telescopes in space, say 16 meters in diameter. And of course, there are very large ground-based telescopes up to like 30 meters in diameter. And adaptive optic technology is coming along in terms of ground-based telescope capabilities. So I'd say the future is bright for, the science of astronomy, for astrophysics, for understanding, and we still know that there are puzzles, there are unanswered questions of physics that have to be worked on. And I think both in the ground and from space, each doing their own thing that they do best, there's a bright future for space astronomy.
One of our viewers asks, what are you most excited about with the future of astronomy? You know, of those great questions and puzzles you just alluded to, which would you like to be solved, and what technology might solve them?
I would like, before I depart this earth, I would like to see evidence of the existence of life forms on another planet. Doesn't have to be Star Trek, doesn't have to be, um, you know, humanoids of any sort. Bacteria will do fine. I just would like to see evidence that life has evolved elsewhere and that we're really not alone in the universe.
Hmm. Another viewer has asked, how long was Hubble supposed to work after it was first launched? Was there a limit on how long you thought it would last?
So long as shuttle servicing was possible, there was no limit in principle. Now, when Hubble was first launched, the lifetime that had been set fairly arbitrarily, I think, was 2015. I'm sorry, I'm wrong. 2005, 15 years is what I'm thinking of. So it's launched in 1990, operates for 15 years. And then after a while, it was determined that if servicing would stop in 2005, but Hubble observations could continue, Hubble operations could continue for another 5 years till 2010, so long as it didn't cost all that much money. Now, it turned out because of the Columbia accident that our final servicing mission didn't happen in 2005, it happened in 2009. The James Webb Space Telescope has not come along as early as people had hoped. And so it's been, in a sense, a silver lining, a small silver lining on the dark cloud of the loss of Columbia, that our servicing mission, the final one, was delayed as much as it was. And we've been around and had the good fortune of staying healthy all the way through the 30-year mark, with James Webb hopefully now to be launched next year.
One of our viewers has asked, you know, after Hubble is no longer operational, is there any point to trying to do another servicing operation, or is it time to just end the miraculous life of the Hubble Space Telescope?
Okay, Hubble will continue to be unique for quite a long time, particularly in ultraviolet wavelengths. James Webb certainly is not designed to observe in the ultraviolet, and Hubble will also continue to be a very powerful optical wavelength observatory. James Webb can do some observations at those wavelengths, but it's not really well instrumented for that. James Webb is an infrared observatory, and Hubble complements it beautifully. So there are many people who think that another servicing mission would be a good thing. Of course, the shuttle doesn't exist anymore, so you would have to figure out a way to do it, possibly robotically, as Frank Sepulveda had envisioned during those years when we were down and worried about the shuttle program.
And we've seen a lot of advances in robotic servicing since that time.
Yes.
You know, we know that multiple companies have been working on robotic, you know, in orbit servicing of satellites. So, you know, who knows? Perhaps something will be available at the time.
Yes.
We have another question, which is, what do you believe is the most remarkable discovery by Hubble? Do you have a favorite?
Oh, I think for sure the acceleration of the expansion of the universe. It was obviously, certainly not my field of physics, but my physicist buddies seem so bewildered by this that it has to be the greatest thing Hubble did, just to perplex these really bright people. The problem is that the more people look into what may be causing the acceleration, what is the negative gravity, as it were, that is causing the universe to speed up instead of slow down in its expansion, the more puzzling it becomes. The more likely, most likely explanation is what was called Einstein's cosmological constant. Now, this was a parameter that Einstein introduced into the equations of general relativity because he thought the universe had to be static. And if you didn't have something that was a retarding force, the universe would simply collapse in under its own gravity, collapse in on itself, And that was unpalatable to Einstein. He wanted the universe to be static. Well, in fact, Edwin Hubble made it clear to Einstein that the universe was not static, but was in fact expanding. And so he called the cosmological constant his biggest blunder, or words to that effect. Well, now we're finding that cosmologists and physicists want to put Einstein's cosmological constant back into his equations, because it turns out that you need some force to cause the expansion to accelerate rather than to slow down under the tug, the mutual tug of all the gravity of all the objects within the universe. What's causing it to speed up? And it turns out that the deeper they look into this, it looks like it's exactly Einstein's cosmological constant. I swear the guy didn't come from this earth. I think he's the first alien.
We have a question about one of the images that you used in your slideshow. There was an image of a black hole that looks like it has color. And this viewer is asking, how is that possible if black holes trap light?
Okay, let's see if I can go back there real quick. Yeah, so I think he's talking about this. Mm-hmm. So what this is really is a galaxy, and you're putting the slit of the Space Telescope imaging spectrograph across the center of the galaxy, and then you're taking, because it's an imaging spectrograph, you can take the spectrum or the distribution of color with wavelength at various spatial points across the diameter of the galaxy. And so here you would have stars far away. Here you would have stars far away from the center. Whoops. But as you got closer and closer to the center, the rotation of stars around the black hole would speed up. And the Doppler shift would cause the wavelength of the light to, in this case, go toward the red, shift toward the red as the stars are moving away from us, or on this side, shift toward the blue as the stars are moving toward us. So in this case, you're dealing with the rotation, with the orbits of stars around the central black hole. In earlier observations I mentioned with the faint object camera, they actually found a disk of gas surrounding that supermassive black hole in M87, and they were able to observe the Doppler shift of the spectral lines emitted by that disk of gas. So no, you're not seeing the black hole. No, you're not seeing colors in a black hole. You're seeing the gas surrounding the black hole that has been compressed and heated as it falls in toward the black hole. And as it speeds up faster and faster in its rotation around the black hole, you're seeing the Doppler shift produced by this heated gas. Or in some cases, you're seeing the color of stars being shifted.
So we have a question about the expansion of the universe. And the question is the universe expanding from the center out, or is it expanding in some other way?
There's no center and there's no edge. It's hard to comprehend this. It's not intuitive at all. When I was in graduate school, I thought of it, I was taught to think of it as an expanding loaf of raisin bread. That was basically a very, very large loaf of raisin bread. So you didn't have to pay attention to the pan. You have to pay attention to the boundaries. So we're deeply buried inside this loaf of raisin bread, sitting on a raisin. And wherever we look, we see other raisins expanding away from us. And the farther the raisin is that's away from us, the faster it expands away from us. This is a characteristic of a uniformly expanding system. And you can think of space-time, which is what we're talking about now. We're not talking about a three-dimensional space. We're talking about four-dimensional space-time as an entity that is expanding itself. And so that raisin bread analogy sort of explains how Hubble's law works. We're not at the center of the universe, but wherever we look, things look like they're moving away from us faster the farther away they are. But if we were on some other raisin, we'd get the exact same result. But you can't think of it in terms of a center or an edge. You can think of it, if it's possible to think of it intuitively at all, you have to think of it as space-time and in four dimensions.
Sure, that's not too hard. Now, we have a question maybe that's a little bit more down to earth. Is the Hubble a reflective or refractive telescope?
It's a reflective telescope. It's called a Ritchey-Chrétien telescope. And what that means is that the surface figure of the primary mirror and the surface figure of the secondary mirror are hyperboloids. They're the shapes of hyperbole, which you may remember from geometry class, or maybe trigonometry it was. But in any event, in this particular optical configuration, some of the aberrations that a telescope normally has, particularly a kind of aberration called coma, is corrected because of the way the telescope is designed.
Mm.
It's a reflecting telescope.
Yes. So thinking about, you know, the long life of Hubble and your career with it, what's the single greatest lesson, positive or negative, that can be applied to future spaceborne telescopes and space projects?
Well, I think the major lesson is don't give up.
Mm.
And the second major lesson is no matter how hard you plan, how hard you try, how much money you set aside, how much time you allow, you're going to get bitten by some law of nature that says if anything can possibly go wrong, it will. Mm-hmm. And so that happened to Hubble in the 1980s, where we had very significant budget and schedule issues that caused us to be delayed. And that certainly happened to the James Webb Space Telescope that has had its own budget and schedule issues. I just tell my Webb friends on James Webb, hey, the same thing happened to us. Mm-hmm. And it just seems to be a rule of major space projects that it's not unheard of. People do bring in their projects on schedule, within budget, and able to do fully everything they were originally promised to do. But on a very particularly big project like Hubble or James Webb, where you're really getting into the unknown, it's just very hard to predict what can go wrong. And so patience and certain humility, and don't give up even if things don't look like they're working out for you.
That seems like good advice. So we have a question, you know, again, about the potential servicing of the Hubble. So without a spacecraft like the space shuttle, how would later repairs be done? We've mentioned, you know, robotic methods could potentially be used, but what about any of the other human spaceflight capsules that are being used now? Is there any chance that those could be used? It doesn't seem like they have the same capabilities as the shuttle.
Yes, you would have to adapt them, but I really believe that some of the technology that is available now, both the private missions that are becoming adapted to human astronauts, and the SLS, the Space Launch System that NASA is working on, the big system, and its manned vehicle. I think it's possible to create configurations of systems like this that would allow you, for example, to create an airlock that an astronaut could move in and out of, and create a platform on which you could mount the observatory or the satellite on which you wanted to work. So yeah, I think creative people could come up with ways to use resources that are already available to us or are already in works to find a way to service Hubble with astronauts. Mm-hmm. But I don't think there's a lot of popularity for that idea within NASA.
So we have time for just a couple more questions. And again, thank you to our viewers for sending these questions in. We hope you're enjoying this conversation as much as we are. You've mentioned this in your talk, but this idea that Hubble is seeing very far and very deep into the early universe. I mean, that's kind of mind-blowing, I think, for most people when they first learn it. And you've mentioned that you've seen pretty close to the very first moments of the universe, to that Big Bang moment. I mean, you know, it's just so difficult, I think, for folks to wrap their minds around that. I mean, how is it that looking out is looking deep into earlier times.
Right. So it's been known for quite a long time that light moves at a finite speed. Light does not travel with infinite velocity, about 300,000 kilometers per second, as I recall, or 186,000 miles per second. Am I right, by the way? Correct me if I'm wrong in my doddering old age. So basically, the farther away something is, the longer it takes the light it emits to get to us. We see sunlight that was not, when we see the sun, we're not seeing the sun as it is instantaneously right now. We're seeing it as it was, 8 minutes ago or something like that. When we look out at the distant planets in our own solar system, we're seeing them not as they are at this instant, but as they were, hours ago. Because it took signals, took light, or took radio signals, for example, from spacecraft on Mars. It takes a little bit of time for the signal to get to Earth. Now, when you're looking out across the universe, you're talking about billions and billions of light years. And it takes billions and billions of years for light to travel across the universe to get to us. Now, here's the thing to understand. 13.8 billion years ago, the Big Bang occurred, give or take a few 100 million years. We're not seeing today where those objects are that emitted the light when the universe was first created. We're seeing them as they were 13.87 or 13.8 billion years ago. Or in the case of Hubble, we're seeing a Hubble Deep Field that may be penetrated to within 400 million years of the Big Bang. So it's something like 13.4 billion years ago. But we're not seeing it as it is right now. We're seeing it as it was 13.4 billion years ago. Meantime, the universe has continued to expand. As that light travels for 13.4 billion years, reaching us, the universe has kept going. So the question is, how big is the universe today? We can see out to a radius of 13.4, 13.5 billion years with Hubble, which is the distance at which the objects that emitted light were when they first emitted that light and that we're now receiving. But really, the universe has expanded beyond that while in the interim. And the number I have heard is something like of order 40 billion light years. So those objects that emitted the light 13.5 or 13.4 billion years ago are perhaps out about 40 billion light years now. And of course, we can't see that far. So within this very large universe, don't know if it's infinite or not, but in very, very large universe, you can think of a little sphere having been carved out with a radius of 13.8 billion years. And that's the farthest that we can possibly see over the age of the universe.
Wow.
Does that make sense?
As much as it ever has to me, that made sense, yes. So that's all the time that we have. So thank you again, David, for joining us. Thank you for a wonderful talk. And thank you to everyone who tuned in. It was really great to have you here. And we'd love to have you in person in the museum, but we love just as much having you in these virtual formats. So thank you for your questions, and thank you for tuning in. And thank you also to our sponsors this evening, the Space Telescope Science Institute and the Hubble Space Telescope Project at NASA Goddard Space Flight Center. And again, David, thank you so much.
My pleasure. Thank you.